Alrighty, so today we're going to continue talking about X-ray imaging and in fact go into how X-ray imaging evolved over time, how it improved. So if we remember from last time, the way X-rays were produced was through the use of a Crooks tube, which is basically a glass tube that kind of looks like this. And what we found was you basically had a cathode and an anode. The cathode allowed for, when of course plugged into a power source, allowed for the bunch of negative ions, electrons basically, to build up on that, circular plate. And the anode had the positive potential. Basically, the fact that the electrons all gathered to the other side meant this side of the wire became more positively charged. And as you increase the voltage, you made the attractiveness of the anode side for the electrons very, very high. And so eventually you'll have an electron shoot off and try to collide with the positive plate, the anode. And that goes, by the way, to show that there are two ways of controlling these electrons. Number one, you could change the voltage. And by changing the voltage, what that does is it makes it more or less attractive for these electrons to be sent towards the positive plate. And so by increasing the voltage, you get higher energy electrons. That is to say, they are more attractive to the positive plate, and so they will move towards that plate faster. And if the electron is moving faster, it has more energy when it collides with the plate and produce the photons, which is what the X-rays are actually are. Those photons then will be higher energy photons. The other option is to change the current flowing through this Crooks tube. And what the current does is a higher current means more electrons are moved through the circuit. And so more electrons will be sent to the anode. If more electrons are sent, then you'll get more X-rays coming out. So by increasing the current, you get more X-rays. And so those are the two options for basically an X-ray technician when they're trying to take the images of a patient. Depending on what it is they're trying to image, if the thing they're trying to take a picture of is more dense, or at least you have to get through part of the body which is more dense, then you need to increase the energy. You need to make it so these X-rays can penetrate further into this material. And in order for an X-ray to penetrate into a material, it has to be of higher energy. So an X-ray technician can increase the voltage of the X-ray machine, allowing for the electrons to be more attracted. They move faster, they have higher energy, so when they collide with the plate and create an X-ray, that X-ray will be of higher energy. Or the other thing that can be done is if you want more resolution, or I shouldn't say that, if you want more, if you want it to be quicker, let's say, that's an easy way to think about it. In order to take the picture, you need enough light on the film to create the image. If you don't have a lot of light, then the image will be very dark and it's hard to see. The more light you have, the better it is to see the image. Well, if you don't want to sit there like they originally had to do when X-rays were first used for 20 minutes, that is, some of the first X-ray images that exist took upwards of 20 or 30 minutes to produce because the X-rays just weren't produced fast enough. So you had to wait for enough X-rays to hit the film to create the image. Well, now we know, of course, if we increase the current into this machine, that'll allow more electrons to be sent away. More electrons being sent means more X-rays will be produced. And if more X-rays are produced, that's more light hitting the film at once. Now, how about how the X-ray imaging evolved? So obviously the original Crooks Tube was very inefficient in making X-rays. It can do it, however, number one, as I said in the previous lecture, the majority of the electrons that were sent through this tube did not hit the anode and instead collided with the wall of the Crooks Tube and basically splattered into the glass and just created heat. And so every one of those electrons that does that is a missed opportunity. And in fact, the vast majority of the electrons did that. Only a very few were lucky enough to hit the anode and create X-rays. So they had to redesign this Crooks Tube to allow for a more efficient process of creating X-rays. And so the first evolution was to say, look, if we're having a hard time sending these electrons to hit the anode from the cathode, well, why in the world do we want to put the anode offset like this so the electrons have to turn to hit it? How about instead we just align the anode straight across from the cathode? And that way, when an electron is sent, it's sent directly towards it, and so every single electron will hit. And in fact, that was the first evolution. They moved the anode to be directly across from the cathode, and thus much more efficient at producing X-rays. However, here's the issue. What wound up happening was, even though these electrons hit the target and produced X-rays, those X-rays were able to basically scatter in all sorts of directions. And so this is bad because what's usually happening is you have your nice little film over here, let's say, and you're waiting for these X-rays to hit the film to create the image. Well, obviously the majority of these X-rays out here are missing the film. And so while you're more efficient at creating X-rays themselves, you're not efficient in directing those X-rays to where you want them to go, which is the camera, the thing that's creating the image. And so it had to be figured out how to redesign this and allow you to more able predict, or at least control, where these X-rays are going to go. So the next evolution wound up being a pretty interesting design. They kept, of course, the cathode the way it was, and they, of course, left the anode straight across because that's a very good way to do it. However, now what they did was they designed the anode to be kind of wedge-shaped. And the reason they did that was because now when an electron was sent across and hit, it hit this angled surface, and thus, when the X-rays were produced, they were all directed in the same direction now. just because of, angle of incidence is angle of reflection. If you have an angled surface, then you can predict where the reflection will be, and thus, now when you have your film, a great number, if not all, of the X-rays will now hit the film instead of being directed away. And so that was a very good enhancement. Number one, move the anode to the other side so that all the electrons can hit, or at least the vast majority. Very few of them will miss now, and thus you're very good at creating X-rays when the electrons are sent. And number two, shape the anode in such a way as to direct the X-rays which are produced in this collision towards where you want your film to be. But there are still some issues. It still was taking a little bit of time to create these images, even though they had increased the efficiency from where it was at the beginning. It still took a while. And so what they wanted to figure out was, how do we increase, without being so completely energy inefficient by changing the current way too much, because you can only change the current until you actually melt the wires. Wires allowing the current to flow through can only accept so much current before they're melted. The friction of the electrons passing through is just too great. And so what they wanted to do was to produce more X-rays, but there was a limit on how high this current can go. And so how can we produce more X-rays? Well, if we had more electrons to send, we'll get more X-rays out. And so they designed a new cathode, which was way more efficient in producing electrons. So of course we still have our anode over here, the positive side, wedge-shaped to direct the electrons. But now the new cathode was basically a filament, like what's in a light bulb, a spiral or a helix, a coil of wire. And so what this allowed to happen is what's called thermionic emission. Fancy term, just to say, thermionic obviously has to do with heat. This is a way of allowing heat to produce electrons. And so this is exactly what the old school light bulbs, that, well, of course, when I was younger, that's all we had, incandescent light bulbs, before LEDs and the like. And that is, there's a metal filament, a little thin coil of wire, let's say. And as the electrons are sent through, because of the shape and the size of the wire and all of that, those electrons produce heat in this material as they go through, just because of friction. And it gets hot enough so as to make the metal of the filament, the coil itself, glow. If you've ever seen, for instance, a metal pan get hot, or if you have an electric stove and you've seen it turn red, glow red, or even charcoal, when it's lit, glows red. The reason it's glowing red is because it's so hot that energy is, the molecules or the nuclei themselves, the atoms, are so hot, they're extremely energetic. They have way more energy than they need. And so when they try to get back down to their ground state, they send out that excess energy as light. And that light is high enough energy, because it's so hot, that it's of a frequency which is visible light. And so that's what's being done here. You have a coil of wire. You send the electrons through, you send a current through, it gets hot enough to basically boil or excite all of the electrons in this metal filament to produce a cloud of electrons around the filament. And then, of course, because there's still this voltage, this potential between the cathode and the anode, we, again, have a whole bunch of electrons being sent through now, instead of, let's say, one at a time or something. And so, of course, we get way more X-rays produced all at once, which will allow for X-ray images to be produced quicker. You don't have to wait so long to get your image made. So that was a great, great enhancement. Instead of waiting 20 minutes, you can now get an X-ray image in, half a second or something. So very, very good. However, this created a new problem. There were so many electrons being sent across at once, with such high energies, that it actually started to wear into the anode, the wedge-shaped anode here. These electrons keep hitting the same surface over and over and over and over again. Well, that basically creates a lot of friction, creates a lot of erosion of the material. And so what winds up happening, so here's a little zoom in thing, is instead of a nice flat surface, you start to get ridges in the face. And this is bad because when an electron hits, now instead of being reflected exactly where you want it to go, it depends on where on this face it hits. If it hits here, it'll be directed this way, but if it hits here, it's directed back that way. Now the surface isn't smooth. You don't have that nice mirror's edge to reflect everything exactly where you want it to go, because the surface is now rough due to you wearing it out with these electrons. It starts to create, it's almost as if you've unfocused the light. You had a good camera where the light was focused by the lens onto the film, so you had a nice clear image. Now, the lens has been distorted a little bit in a sense, and thus the light hitting the film is not focused like it used to be, and you get more blurry images. Or, if you do get a good image, it takes longer because the electrons start to miss again. So there was one more upgrade that had to be done, and here's what it looks like. They kept the thermionic emission because this was very, very efficient at creating the electrons. However, the anode now, they designed in slightly new way. They liked the wedge shape to direct these X-rays where they needed to go. However, they had to come up with a way for these electrons to not keep hitting the same spot over and over again. And so what they came up with was a pretty interesting concept, and that is, well, what if we have something that looks like this, and it can spin? So what that allows to happen is you have an electron, it still hits the wedge surface and gets directed downwards, let's say towards the film, but now it's also spinning, so that as time progresses, you're hitting different parts of this wedge-shaped anode. You're not always hitting the same spot. If it spins, you're always hitting the wedge, an angled piece, but it's a different part of the wedge. And so this was the final evolution, basically, to what we have today, into how to create X-rays to make an image. You have the negative side over here, basically a cloud of electrons boiled off of this filament. The other side, positively charged, attracting those electrons. You fiddle with the voltage and the current to get the kind of image you want, depending on how deep you need to be able to tunnel into, and how good of an image you need, how clear. And then you still have your positively charged plate over there, the anode, spinning in wedge shape, directing these X-rays to the film. And so you get nice, clear X-ray images at little time and not having to spend too much energy to do it. So I hope this makes sense. I hope this is clear and gives you a sense of how, over time, X-ray images evolved. Also, it's important, as I said, to understand how to adjust the options for your image. You know, are you trying to look into the chest, into the heart, or somewhere in that region? You may need to be able to tunnel into the material of the body further, and thus you may need to increase the energy of the X-rays to be able to go through further. And so you increase the voltage. Higher voltage, you're attracting the electrons harder, they move faster, and thus when they stop, because they hit the anode, the X-rays which are produced are much more highly energetic. And of course, if you want to get a faster image, or you need to have more light, quote unquote, shining onto the film, you can increase the current to make more electrons go through per second. Anyway, that's all I have for the X-ray images. I hope this makes sense. And until next time.